the video, we'll be showing that if we have any principal ideals domain R, then R is necessarily a unique factorization domain, and the Bezout's equality holds therein. Now, onto the proof. We shall show first that if R is a principal ideals domain, then it is a UFD. We know by the unique factorization domain characterization, or we call it something like this, that a commutative ring is a unique factorization domain if and only if the greatest common divisor function exists, that GCD exists, is well defined, and that there doesn't exist an infinite sequence of a non-trivial divisors, right? So we shall show that this holds for the principal ideals domain, and we shall thus obtain this unique factorization domain. Now, part 1. Choose some AB from the commutative ring, and denote I to be AR plus BR. Now, since I is a principal ideals domain, meaning that it has only principal ideals, there surely exists some C. There surely exists some ideal containing AR plus BR, and since it's a principal ideals domain, there must exist some element C such that. So now I shall take the liberty to remind you that some U divides V if and only if the principal ideal VR is a subset of the principal ideal UR. This was actually one of the motivations for even constructing something like an ideal. But anyway, it must hold then that since AR is a subset of CR and BR is also, then by this that C divides A and C divides B, so it's a common divisor. Now, if we consider some random divisor of both A and B, and of both A and B, so let D be such, or D in R be such that D divides A and D divides B. But by the previous characterization, this means then that AR is a subset of DR, and so is BR. Because I is the sum of AR and BR, this means that DR is a subset of I. Oh, pardon me, I meant superset of I meant that superset. So thus we have that CR isn't subset of DR. Well, this of course is I, and from this follows then that D divides C. Thus we have that C is the greatest common divisor. So thus C is the greatest common divisor. Moreover, we have that C is a subset from the construction, really. What is it? Alright, from here, that C is an element of AR plus BR, and as such, C is equal to some AR plus BS, say, for some RS in the ring. And of course, this is the Bezout's equality. Alright, so thus we conclude part 1, and we can go on to part 2. So, for contradiction, assume that there existed such a sequence of infinite divisors. So, assume, as we have such an infinite sequence of divisors, then necessarily, again, by this property, we have that A1 R is a subset of A2R, is a subset of A3R, etc. So we have this infinite sequence, well, we have this nested sequence of ideals. But we know by the previous theorem, that being the ideals arithmetic theorem, that this forms an ideal. So the union of these exists and it is an ideal. So denoted I. But since we are operating on a principal ideals domain, this means that this itself is a principal ideal domain, and thus there must exist some element, call it B. We now observe, however, that B actually is from a smaller set than the commutative ring itself. It must be a member of I, because the union of these ideals does not contain any element from the outside of all of these ideals, and as such, the generating element must be contained in their union. So B is an element of I, but then this means that there must exist some index such that B is contained in I indexed by this index. But then we obtain the following absurdity, that BR is a subset of this A1I, which is a subset of AI plus 1I. Oh, of course, R's is an element of, etc. And this all is an element of I. But this is the BR. So BR is a proper subset of itself, which is laughable. So this is a contradiction, and thus we have proven there doesn't exist any such sequence. And as such, the characterization of a UFD is satisfied. And as such, we have shown that the commutative ring R is a UFD. And thus we conclude the proof. Also, I should have used improper. I should have used proper subsets. This is because of this. Pardon me.